Hey guys, let's rehash something we just got finished talking about. What we illustrated in the previous video was the fact that I could utilize variants to be able to do unequal cost load sharing across prefixes that have been installed inside of my topology table, provided nothing was worse than 128 times as bad as the feasible distance calculated for my successor route. Now, what I want to point out here is the fact that we also can employ this same concept for the purposes of being able to do traffic engineering. So let's remove both of the configurations that we have in our topology right now. What we'll do is we're going to cut over to, let me go ahead and just erase some stuff here. Let's cut over to R22. And on R22, I want to remove that variance command. Don't want to do that anymore. So config T, router EIGRP 10, no variance 128. I could have said variance 1, do show run section router EIGRP. See, we got the metric weights. I'm going to go ahead and fix that too. So I want to turn that off. Let's see. We've got quite a few things still left in here as far as artifact configuration, but it's not going to affect us in the long run. And let's go to R2 and let's disable this delay. I'll just simply say no delay. And that was 16,777,215. And now let's see if we do any load sharing. Show, or actually we'll just trace route real quick. Trace route to 11, 11, 0, 11, and we should be load sharing, which we see that we are. Now, inside the context of CCIE, routing and switching, version 5 studies, we need to know any tool available to us to be able to do or manipulate how traffic is going to travel through our infrastructure. Now right now I want to illustrate a point, and that point is the fact that we're not using bandwidth, so we need to fix that. So what I'm going to do is I'm going to adjust my K values. So all I'll do is I'm going to say do or show run interface or show run section router. I'm going to grab my K value manipulations here and I want to change it. So I'm going to say config T, router, EIGRP 10. I'm going to say, paste that in there, and I'm going to turn K1 back on. That's going to affect all of my devices. So all I'm going to do is I'm going to grab this, and I'm just going to do it on all of my devices real quick. So config T, router, EIGRP 10. Oh, I'm on named on. Hold on, is in use. Oh, that's R1. Router, EIGRP named, address family, IPv4, unicast, autonomous system 10, plug that in there. So let's go to R2, do the same thing, router, EIGRP 10, plug that in, 3, plug it in, 4, I'm not running it on, I'm not doing anything with 4, nor am I using 5. My cats are next, so cat1, config T, router, EIGRP named, address family, IPv4, unicast, autonomous system 10, and paste it in there. Lost it. Keep grabbing this stinking thing. Bear with me. Metric weight 0, 1, 0, 1, 0, 0. Cat2 metric weights 0, 1, 0, 1, 0, 0. All right, everything should come back up. Let's go over to R22 and do a load test. Do a trace route again. Let's see if we're actually going to load share, and we're using R2 and R3. Show IP route for 11, 11, 0, 0 / 24, and we're good to go. Our share count is 1. We're not doing any type of manipulations. Let's take a look at our topology table. Show IP EIGRP topology table for 11, 11, 0, 0 / 24. and we have both of our entries in here, and our metrics should be, composite metrics are going to be much, much higher because now we're actually involving our bandwidth and our delay computations. So what I want to do is I want to illustrate the fact that I have two different ways that I can manipulate how traffic would traverse our infrastructure. So let's operate on an assumption. Let's say that I do not want traffic to go through R2 unless my link to R3 goes down. So in other words, what's going to happen here is I need to make certain that R2 is not going to be preferred. We already did that, and we used delay. I'll just repeat the process in case that was a little while ago for you guys with regard to being in a video. So what I do is I interface, do show CDP neighbors. I want to look at the device that's connected to Cat1. That's going to be via Ethernet 03. So interface E03. And what I'm going to do is I'm going to manipulate my metric using delay. So show interface E30 pipe include delay. Show IP or show. Do show interface oh, wrong one. Pipe include delay. I never can remember if delay is capitalized or not. DLY. So apparently I can't remember if it's abbreviated or not. Include DLY, and it tells me it's 10 microseconds. So let's go ahead and change that. Let's just double it. Config T, interface E03, and we'll say delay. And remember, I'm going to put it in tens of microseconds. So if I want to double it, it would be 200 tens of microseconds. And now what I'm going to find when I cut over to R22, I should only have one prefix being used in my routing table. Let's look at these metrics. So notice I've got 21, so no, excuse me, I got 2195744, and I've got 2221344. So bear in mind, the lowest is going to be the one that is used as my feasible distance. So my feasible distance should be 2195744, which it is, which means I only have one successor. Now that means, since I only have one successor, I only have one entry in my routing table. Show IP route EIGRP, actually no, we'll say 11.11.00/24, and I only have the one entry via serial 20. But what happens if I lose serial 20? Config T interface serial 21 shut. Now the moment I do that, what ends up happening is that I do not have to rerun the diffusing update algorithm. Because what happens is the reason that I have the feasible successors is the fact that if I lose the successor, I can immediately just do a local change and start using that without having to run a computation. If I don't run any computation, that means I'm not sending any queries. Now, if I do not have a feasible successor in my topology table, then what's going to happen is I need to recompute that route. So I'm going to go active on that particular route. I'm going to send queries. I'm going to have to wait for my EIGRP environment to reconverge. But as long as I have an available entry in my topology table, I do not have to do a computation or a EIGRP system-wide computation. I just simply install it in my routing table, and it shows up almost instantly. So do show IP route 11.11.00/24. Notice now 20 is in use using that higher metric. So no shut. That's going to force me to redo the computation. And now notice it's changed to 20. Or 21. We'll watch it. See, the link hadn't come back up yet. There's my adjacency. And now it's 21. So using the 2,195,744. So that's going to be how I do this manipulation using delay. Now remember, so long as I have that entry in the topology table as a feasible successor, then I could do that on equal cost load sharing, and this would be kind of moot. But another way that I can manipulate this is to change the bandwidth. Let's take a look at that. Now, where am I going to change my bandwidth? First of all, let's remove my delay command on R2. Say no delay 200. Cut back over to R22 and let's see if we are load sharing again. And we are. Notice my metrics are now identical. So when I go in here now, one of the things that I could do is, let's say I want to change my value here. I don't want to use R3 unless R2 goes down. And the only command that I can use to do this is going to be bandwidth. So let's take a look at how we would manipulate this. So I'm going to go to interface, serial 2/1, and I'm going to use the bandwidth command. Now notice my bandwidth is entered in values of kilobits. But what is my bandwidth? Do show run interface serial, or do show interface, excuse me, serial 2/1. Scroll up just a little bit. And I see that my bandwidth is 1544 kilobits per second. Now, if I did not want to prefer S21, which is leading to R3, I need to increase or make the bandwidth worse. So what I'll do here is I'll say bandwidth, and I'm going to say 128 kilobits per second. Now let's look at my computation now. So if I execute the do show IP route, notice I now only have one entry, and that entry is going through R2. Now what happens if I cut that down? If I turn it off? Well, first let's look at our topology table for that same route. Show IP, I'll just type it. Do show IP EIGRP topology table for 11.11.00/24. Now notice I still have both entries. It's just one is better, one is worse, and I'm using the best one. And the best one is going to be the prefix, let's see, that's going to be 2,195,744. This one is going to be 20 million. So obviously we're going to use this one. This is going to be our feasible distance for our calculation, 2195744, which means we're going to use the link through serial 20 to reach those prefixes. I can illustrate that. Do trace route to 11.11.0.11, and that's what we're going to do. We're going to go through R2, but what if we lose that prefix? So interface serial 20 shut. See if I can't repeat that do real quick. And notice now we're going through R3. So that process was almost instantaneous as a direct result of the fact that we had a feasible successor in the topology table, which means it's a prefix we learned from a device that has an administrative distance less than our feasible distance that's been locally computed on our device itself. So with that being said, we can see how we can use the idea of bandwidth or delay to affect metric computation for the purposes of ensuring that we have some administrative control over how traffic is going to be engineered or how traffic is going to transit our infrastructure. And remember, I changed the bandwidth locally on R22. And we also need to pay attention to the fact that when you're experimenting with this in labs, put it in different places and see if it actually directs or affects the computations with regard to how we're learning or how we're actually building out this idea of the composite metric. So with that being said, I'll see you guys in the next presentation where we're going to be talking about with regards to convergence timers. We want to know how EIGRP is going to use timers to determine when we have routes that have died, when we have the idea of being able to refresh our neighbor relationships, and we're going to entertain the concept of the finite state machine. I'll see you guys in that video. Bye-bye.